Okay, so hello everybody. My name is Lilian Navarro, and I'm going to be one of the co-hosts for this GEO seminar. And this is a wonderful opportunity that we have today because it's a GEO seminar that is actually a collaboration between GeoLatinas and the Education and Outreach Committee and the Paleo-PERCS Steering Committee. For GeoLatinas, we are going to be as a co-host, myself and Clara Rodriguez. And from Paleo-PERCS, the co-hosts are going to be Chrissy Hall, Pedro Godoy, and Natasha Secom. We are thrilled that the person that is going to be doing this GEO seminar is Sofía Barragán Montilla. Her presentation is about the North American paleoceanographic climate change lesson from the recent past. And she is a Colombian geologist from, she graduates at the National University of Colombia. She is specialized in micropaleontology, and she completed her master's in applied geology from the University of Zaragoza in Spain in 2018. She has been working as a micropaleontologist in the oil and gas industry for 4 years. And since 2021, last year, Sofía has started her PhD project from the Cluster of Excellence of the MARUM Institute at the University of Bremen in Germany. Her research is groundbreaking because she is focusing on studying changes in the bottom water conditions of the Eastern North Atlantic. She is looking at those changes which are associated with major paleoceanographic changes during the last deglaciation. Since 2019, she is one of the greatest members of GeoLatinas. We are very proud of the work that she is doing in geocommunications. And at the same time, she is contributing in earth science and others, other initiatives in GeoLatina and other organizations, and she is trying to bring up a more inclusive and diverse place. So without any more introduction, I'm going to, can we change, can we, someone give her the shared her screen?
I forgot to unmute myself, I'm so sorry. Okay, so you can hear me okay? Yeah?
Yes.
Thank you so much for the introduction. No pressure for me. I'm very proud to be a part of GeoLatinas, and I'm very thankful for both of you to give me the opportunity to present what I have been doing in the last year and a half here at the MARUM Institute. And I want to say first that my background, as Lilian already said, is on benthic foraminifera taxonomy and polyecological reconstructions. So for my PhD, I wanted to step out a little bit of my comfort zone, and I jumped into a geochemical process, also in benthic foraminifera. And before I start telling you what I'm doing here, I want to stress that this investigation is being funded by the German Research Foundation through the Cluster of Excellence here at MARUM Institute in the University of Bremen. And I'm working in the paleoceanography group headed by Dr. Heiko Palike, and my main supervisor is Stefan Litza. And I have a great team behind me that has been helping me carry out this research. But I want to thank especially Dr. Heather Johnston, which is the one that has been helping me with the magnesium calcium measurements and the interpretation of the data, which is kind of the main focus of my research here at MARUM. So a little background story about how did we come to do this research. Initially, I started my PhD here at Germany in January last year, in the worst part of the pandemic. We were in lockdown here in Germany. And initially, the idea was to study the effect of methane seepage in climate change since the last glacial maximum. And for this, we were going to use gravity cores that were collected in the Northwestern African, were going to be collected in the Northwestern African slope. However, the expedition was meant to take place in October last year, and due to the COVID restrictions, it was indefinitely postponed. So we had to look for a new focus for my PhD topic. Luckily, I was already analyzing and published data of a deep core that was collected near the area of interest. And I was also about to start sampling a not so deep core also close to the area of interest. And I have the very big advantage that my area of study is located in the North Atlantic. As some of you may know or not, there are many processes in the Atlantic Ocean that are actively modifying climate change, and they're very important for us to understand them in detail. And one of these processes is the Atlantic Meridional Overturning Circulation that we call AMOC for short, because it's a quite long name, really hard to pronounce if you're not a native English speaker. But in a very oversimplified way, what AMOC does is that it takes the heat that is being absorbed by the ocean and it distributes it globally through this overturning circulation. So in very few words, what it does is preventing us to warm at even higher rates. AMOC has influence in other processes that occur in the deep ocean, like ocean ventilation and heat uptake. And now, why is it important for us to understand how AMOC is actively modifying these processes in the deep ocean? There has been a lot of concern in the last decades due to climatic models suggesting that for the 21st century, there's going to be a decline or a slowdown of the Atlantic Meridional Overturning Circulation. What these climatic models suggest is basically that due to AMOC decline, we're going to have a warming of the ocean. And given that the heat is no longer being distributed globally, that transported to the poles where it cools down and it sinks again and the whole overturning circulation starts, we're gonna start to see this heat being mixed to the deeper layers of the ocean. So basically what this means is that AMOC has the potential to set the depth of the heat of the storage of the heat in the ocean. However, these models have very large uncertainties, basically because we have a lot of gaps in our information. And the most important gap comes from the fact that we have a lot of data from the surface of the ocean, but we know very little about what's happening to the ocean in depth. To put you a little into context, and very luckily for us, not a very long time ago, AMOC slowed down in the recent past. Most recently, this slowdown is recorded by kinematic proxies, the protecting infrared signal in sediment records. And what we observe is that throughout the whole Atlantic, we see a decrease of AMOC circulation during the younger dryas, approximately 12,000 years ago. This was a slowdown of the AMOC of approximately 30%, which is quite similar to the scenario that climatic models suggest for the 21st century. But also a little bit a while back, we see that during the Henry Stadial that AMOC also slowed down almost to a nearly shutdown scenario. So these two events in the recent past that occurred in the last 25,000 years allows us to study directly what would be the consequences of such a scenario. And putting you a little bit into context of the research, we asked ourselves three research questions that we wanted to solve with the data set that I'm going to present to you today. The first one is how does AMOC influence ocean heat uptake? And this is very important because if it gets to a point that the ocean is no longer capable of storing more heat, and please bear in mind that the ocean accounts for 90% of the excess heat of the Earth, so it takes a huge amount of heat from the atmosphere. But also this heat uptake takes place in the first 2,000-meter water depth. So as I mentioned before, we have a lot of information on the surface, but we don't know what's happening to the ocean in depth. So we want to assess how does AMOC influence ocean heat uptake. We also want to see how the deep ocean is reacting to AMOC variability, what other parameters can be affected by a decline in AMOC circulation. And finally, we want to see what are the actual implications for global climate, given that we have a possible AMOC slowdown scenario for the 21st century. And to respond at least partially to these questions, we have information from two cores from the Eastern Atlantic, which is the ones that I have been studying so far. As I mentioned before, I already had unpublished data that was very kindly provided by Stefan Munitz and Heather Johnstone for a deep gravity core that was collected at around 2,400 meters depth. So we have information of the deep ocean. Just for you to have as a reference, bottom water temperatures at this point today are around 3 degrees Celsius. And also I started sampling last year this core GeoB9508 that was collected at water depth of around 800 meters. So this one is the one that is going to give us information about the intermediate waters. Also, as a reference, bottom water temperatures are around 7 degrees Celsius in this area. So to study the deposits from since the last glacial maximum, which is the time interval that we're interested here, we first had to do our age model, obviously, because we need to know where in time we are. So for this, my supervisor, Stefan Melissa, was the one that used 12 radiocarbon dating for Atlantic foraminifera, and using the Bacon package on R and the INCOD 13 calibration curve, he was able to create a quite accurate and high resolution age model for the sequence that we study for GeoB9508. Overall, what we see is that it's a normal deglacial sequence with no hiatuses or reversals, and it has sediments from the last 43,000 years. So we have a very good, complete sequence to study the effects of AMOC since the last glaciation. And for GeoB9508, I used the same script that Stefan wrote, and we were able to obtain a very high resolution age model using 16 radiocarbon dating from Atlantic foraminifera. Again, this is the normal deglacial sequence with no reversals, but in this case, we only have records from the last 27 years, which is still very good because it's within the time interval that we wanted to analyze. So how can we assess how ocean heat uptake has changed in the past? And fortunately for us, the answer is quite straightforward. We use magnesium calcium thermometry. Just as a very wide explanation, this is based on the assumption that the substitution of calcium by magnesium foraminifera calcified in the ocean depends on temperature. So it's a direct assessment of temperature, either in the surface if you measure them in Atlantic foraminifera, or in bottom waters if you measure in Atlantic foraminifera. And also, when you combine these measurements with oxygen 18 data, you can also give us a kind of a background on how salinity also varied in time. So as I mentioned before, we're interested in what's happening to the ocean in depth. So for this reason, we use Atlantic foraminifera. The methods, in a very general view, we take 2 to 6 tests of Vigorina, we crush them, and we clean them using a specific protocol to avoid contamination during the measurements. The concentrations of trace elements were measured in the ICP-OS here at the University of Bremen. And finally, using the equation by Roberts and Otter in 2016, we are able to obtain the bottom water temperatures for each sample. For the deep core, GeoB9508, we use Vigorina mediterranea, which was the most abundant Vigorina we had in this core and the better preserved. And for GeoB9508, we use Vigorina mediterranea, which was, for this case, the most abundant and better preserved for this genus. We also wanted to see how bottom water ventilation and salinity may have changed during this variability stage scenarios. And for that, for the deep core, we were able to obtain stabilized isotope measurements from Silicitoides wilderstoffi, the one you can see here. And for the intermediate waters, for GeoB9508, we use Silicitoides pachyderma for most of the core, and for the capsule sampling that we have, we use Silicitoides reversonianus. Here are some of the pictures of the sampling and washing of the samples and picking during this time. And I would also like to say that for GeoB9508, I had the opportunity to pick Atlantic foraminifera for quantitative and qualitative analysis. So we also have, additionally to bottom water temperature reconstructions and ventilation reconstructions, we also have a little bit of an idea of what was happening pharmacologically in the intermediate depths. So jumping right into the results, as I mentioned before, for GeoB9508, which is the deep core, the one that was collected at 2,400 meters depth, we have a very nice deglacial sequence with no hiatuses, no reversals. So we were able to reconstruct what happened in the last 47,000 years. One of the cool things about this record is that we were also able to see what was happening before the last glacial maximum. It is not the scope of this research, but it was nice to have it as a reference. From the oxygen 18 signal, what we observed is kind of the global spectrum with glacial signal. But the one thing that I want you to focus on for this core is the reduction on carbon-13 signal, specifically in the Henry Stadia 1 and the younger dryas. This is what is indicating us is that there is a decrease in bottom water ventilation. And at the same time, we observe that there's an intense warming of deep waters in coincidence with this decrease in ventilation. And moreover, there is mass stagnation of the heat uptake during this time. So zooming in into the time interval that we're interested in, the last 25,000 years, I wanted to include here a representation of AMOC variation, which you can see by the changes in the protecting thorium kinematic proxy that I mentioned at the beginning. The red and yellow curves are represented variations in the Western Atlantic. This is data from the Bermuda Ice. And the purple curve is representing data from the Western Atlantic, very close to where our area study is located. It is important to see that AMOC variations are not as intense as we observe in the Western, for the area that I'm talking about right now. But it is important to see that these trends of decreased ventilation that we observe from the carbon-13 signal during the Henry Stadia 1 and during the younger dryas are in coincidence with this declines in AMOC circulation. Most importantly is that during the Henry Stadia, decline was not exactly the same in the western and the eastern part of the Atlantic. What the protecting thorium kinematic proxy is showing is that it happens in two phases during this time. The first one is not so enhanced, and it occurs in the last 2,000 years approximately. And then there is a second phase of enhanced AMOC decline that is also marked by this important decline in carbon-13 signal. Another thing that is very important to notice, and I mentioned very vaguely in the last slide, is that not only we have this 2-degree warming at the beginning of the Henry Stadia and during the younger dryas, we also observe that as soon as this warming happens, the temperatures become more stable, sort of stable. And this means that the ocean is no longer taking up more heat during this time. Coincidentally, during this time is when we have this AMOC shutdown that I mentioned before. And a similar thing happens during the younger dryas. We see a sudden decrease of 2 degrees Celsius, and we have a period of stagnation in ocean heat uptake. Most importantly, and something that I want you to keep in mind, is that for this AMOC shutdown scenario that it is proposed for the Henry Stadia 1, we see that this stagnation lasts for 5,000 years. While for the younger dryas, when we have idea that the AMOC slowdown was about 30%, this stagnation only lasts 2,000 years. So it gives us an idea of how the intensity of AMOC also has an influence on how heat uptake is working in the deep ocean. Another thing that was very fortunate actually is our research a couple of years ago. They measure magnesium calcium radius of foraminifera in the same core. So we also have information of what is happening in the surface. And it is quite interesting because what this research found is that from the LGM time to the Henry Stadia, there is a decrease in sea surface temperature of around 1 to 2 degrees. And this has also been identified with other paleotemperature proxies like Alkanon paleotemperature reconstructions. But another important trend is also that at the same time we have this cooling of the sea surface temperature, this coincides with the intense warming that we observe in the deep water. Comparatively, we also observe that in the Holocene, when we have this restore of AMOC circulation, the sea surface temperatures start to increase. At the same time, bottom water temperatures become cool again. So this is basically supporting what climate models have suggested, that during times of AMOC decline, given that we don't have this heat transport towards the north where it cools down, we have a downward advection of heat. So it is the deep ocean, the one that starts warming and storing all this heat that is usually stored in the sea surface. So we already know what is happening in the deep ocean. We wanted to see if we had the same effect at intermediate depths or we have different behavior of bottom water temperatures. Before I jump into the geochemical process, I wanted to show you a little bit about the results of the quantitative and qualitative analysis of benthic foraminifera assemblages. And it was quite interesting to see that depending on the climatic event where we were, benthic foraminifera assemblages were different. So for example, for the last glacial maximum, we have a specific benthic foraminifera assemblages, and as soon as this time period ends, we have a peak in abundance of Mediterranean and Mediterranean, and we have this first assemblage during the first part of the Heinrich stadium. During the second part of the Heinrich stadium, we have a shift in dissociation, which is mainly dominated by these polypines. And it is very interesting because this timing actually coincides with the two phases of AMOC slowdown that I have mentioned before for the Eastern Atlantic. The same thing happens for the younger dryas. We have a specific benthic foraminifera just for this interval. And finally, for the Eocene, we have a complete shift on the species that are being most abundant during the assemblage. Actually, this is the forum that marks the whole Eocene for the sequence. So benthic foraminifera changes in response to all these global climate changes. But what is the geochemical process telling us? So for the oxygen 18, we observe overall this trend, the glacial trend that is to be expected. However, we did notice that for the boiling Allerod warming after the end of the Heinrich stadium and during the younger dryas, we have an increase in the oxygen 18 seawater signal. We think that this might be pointing to an increase in salinity. However, this is something that I haven't really worked on more. It's one of the things I would like to approach later on. But the most striking feature here is the carbon-13 signal. During the boiling Allerod period and the younger dryas, and actually in coincidence with this increase in oxygen 18, we observe a very dramatic drop in the carbon-13 signal. And what is the explanation of this? We already know for the deep core for GeoB9508, as I just showed you, that these decreases in carbon-13 signal are usually related to a decrease in bottom water ventilation, which is linked to AMOC decline. However, here it's quite different because it happened a little bit after the Heinrich stadium 1. So the two possible explanations are, of course, there is a lower ventilation due to AMOC decline, but also from the trophic level reconstructions that we did using the TRUX model, and this comes from the quantitative analysis of the benthic foraminifera that we found in this core. We observed that during this time, we have an increase in the organic matter content at bottom waters. So we believe that this excursion of the carbon-13 is actually a response not only of lower ventilation, but also of high amount of organic matter to the bottom water. And also in coincidence with this, at the same time, we observed that there is a decline in the oxygenation of bottom water. So we see that all these parameters are connected. And when we, when we observe the bottom water temperature reconstructions for this core, is not quite as straightforward as it was for the deep one. And that is because we don't see this intense deep water warming of 2 degrees Celsius. Here what we observe from the last glacial maximum to the first phase of the Heinrich stadium is a decline in bottom water temperatures, but it's not as dramatic as we expect. It's like 0.5 degrees Celsius maximum. However, for the second phase of the Heinrich stadium, we do see that temperatures start to increase by a factor of 1 degree Celsius approximately. And for the time interval between the boiling Allerod and the younger dryas, we see a stagnation. The ocean is no longer taking up more heat during this time. Once the younger dryas is over and the AMOC circulation is restored, we observe that bottom water temperatures at intermediate depths start to cool down again during the Eocene. So now we have seen how contrasting these results are. And it is interesting because we know that heat uptake in the ocean is not uniform. It's not, we don't store the same amount of heat throughout the whole layers of the ocean. So to show you the big picture of what we found is, first of all, that the carbon-13 changes that we observe in the deep Atlantic are indeed responding to changes in AMOC decline. But for the intermediate depth core, this signal is not only showing this decrease in ventilation due to AMOC decline, but it's also showing a higher amount of organic matter in bottom waters. And there's actually research pointing to an increase in primary productivity in the surface of the ocean during this time. So it might be related to this. But also, and most importantly, we observed that an intense warming of 2 degrees Celsius again in the deep ocean, but this is not as evident at intermediate depths. And furthermore, this warming at intermediate depths occurred a little bit after the deep ocean. So this is what is showing us, in conclusion, is that with variations with AMOC decline, we have variability in where the heat is being stored in the ocean. So basically, it supports the idea that AMOC variability sets the depth at which the heat is being stored in the ocean. So in AMOC decline scenarios, we know that it's being stored more in the deep ocean under 2,000 meters depth or around 2,000 meters depth. While in an AMOC enhanced scenario, we have this heat being stored at the surface of the ocean. It is important to notice too that depending on the intensity of AMOC shutdown, the implications are going to vary. So for example, for the deep core, we observed that during the Henrik Stadium, when we know that AMOC declined nearly to the point of shutdown, this heat stagnation, or this period of time where the ocean no longer took up more heat from the atmosphere, lasted for 4.5 kilometers. While for the younger Dryas, where we have a AMOC scenario slowdown of 30%, we see a stagnation that lasted around 2,000 years. So in conclusion, we see that due to AMOC decline, we had a heat uptake stagnation of the ocean overall, and the implications for this in the future AMOC slowdown scenario is that it will enhance global warming. And what's next? There's still a lot to do. We still have a lot to discuss. This is, I think I mentioned it at the beginning, this is still a work in progress. So any questions, comments, suggestions you may have, they're going to be very, very well received. But for now, what we want to do next is first for GeoB9508-5 we want to measure magnesium calcium fault order species of benthic foraminifera to see if the bottom water temperature reconstructions are in agreement with the ones we measure in the video right now. I also want to dip in a little bit more on the multivariate analysis of benthic foraminifera because they're definitely showing changes in distribution and coincidence to these global climatic events. So I want to see which are the factors that are controlling their distribution in the different time intervals that I just mentioned before. And also another interesting that I noticed from the dissolved oxygen concentration reconstruction that actually I did using transfer function from the benthic foraminifera ocean index is that we see a deoxygenation trend from LGM times to the present. And this is something that has been previously reported by other researchers. So I want to elaborate a little more into that. But most importantly, this interval where we have this excursion of the carbon-13, this stagnation of bottom water temperatures, this increase in trophic levels in the amount of organic matter of bottom waters, occurs in coincidence with this decrease in oxygenation at bottom water. So we believe that it might be related to an extension of these oxygen minimum zones that we usually have in the Atlantic and the Pacific. And we would like to see if it is actually responding to this AMOC variability during this time. I also plan to dig a little deeper into the salinity analysis. I haven't been paying much attention to it because, well, the scope of the focus of the research is more on bottom water temperature reconstructions and the carbon-13 signal. And I'm also right now picking forums from another core, a little bit deeper than the ones I showed you today, is GeoB9508-5. And this one was recorded at water depths around 3,000 meters depth. So we want to see if the bottom water temperature reconstructions show a similar trend to what we observed with GeoB9508, and also to see what's happening with heat uptake in different parts of the ocean layer. And that is it for me. So I hope I was clear. I know it's a little bit confusing. It's a lot of information.
No, you were extremely clear. I think I do have to say that I enjoyed your presentation so much. I For the people who are joining right now in Facebook, you may have found on at the beginning of presentation, we were not able to connect into Facebook, but we are recording the talk and it's going to be available later on in the GeoLatinas YouTube channel, as well as the Paleo Perks YouTube channel. I would like to open the floor. Please make any of the questions that you have in your mind right now and write it down in the chat. We will start discussing them with Sofía.
So turn my video on. So I got some questions. I can read them to you. So first question is, hi Sofía, superb presentation. Question is, what was the impact of calibration curve? What was the impact calibration curve used instead of a marine calibration curve? Where's the impact? Sorry, I can copy and paste it to you in the chat as well, to everyone. So what was the intact calibration curve used instead of a marine calibration curve?
The intact, I'm not quite sure. Okay, yeah, now I get the question. I don't remember quite well, but I think the INCAL is for the Atlantic Ocean. To be honest, this part I didn't work very thoroughly. That was developed by my supervisor. But yeah, it's because it was for the Atlantic. Interesting. For the atmosphere. I'm not sure. I think we did use the marine curve, now that you mentioned it, because we first ran some H models that didn't fit very well. And we noticed it was because we were using the wrong calibration. But at the end, we did use the marine one. So maybe I have to check what I wrote in the presentation. Sorry.
Just a second.
So there's a question in the chat.
Oh, you can, what was
your method? What was the method for oxygen reconstruction? I didn't dip much into it because it's not really the bigger scope of the presentation. But so before I used to do oxygen reconstructions based on the amount of stress species I had in each sample. And sometimes I usually use the benthic foraminifera oxygen index, which are very good for showing changes in oxygenation. But for this case, there was a paper that was published at the beginning of the year. They proposed an enhanced benthic foraminifera index, which is quite cool because the regular one only takes into account disoxic species, while this enhanced one also takes into account suboxic species, which actually for this part of the Atlantic are more abundant. And they also propose a transfer function. So I calculated this enhanced benthic foraminifera index, and then I applied the transfer function. And we also had a good point of control, and that is that the upper sample, the one that the more modern sample, kind of agrees with the data we have about oxygen concentration in for modern times. So yeah, that was the method that I used. It's a very cool paper. You can find it online very easily because there's little been done in the subject. About the equipment to shoot the excellent images of benthic foraminifera. Actually, it's very cool because here at MARUM they have a Kenyan microscope, a digital microscope. It takes, I'm sure Michael already knows this, but it takes picture in different parts. It's like a robot, and then it merges all the pictures and it gives you a very high resolution image of benthic foraminifera, which is quite cool because it's very good for taxonomy.
There's another question that came to me. I'm going to paste it in the chat as well. So I'm just going to read it out loud so people can know it after in the recording. So a quick question. Wondered, how do your finding of mid-depth warming compare to findings from the Henrik studios on the Portuguese margin?
So I guess you're referring to a specific research. I'm not sure. I have read so many papers that I don't know. But from the intermediate water warming that has been reported for the Henrik studio, they're kind of in agreement. Again, the Henrik studio has two phases of AMOC slowdown. For our core specifically, we see this temperature increase during the second phase of the Henrik studio, but it's not as enhanced. We actually see this warming during the boiling hour. So I would have to read the reference you are pointing out directly, but in this case, I would say there's no an evident warming, at least not at intermediate depths in this part of the Atlantic.
Right. We have Bremen monitoring Facebook live stream as well. So if you have any questions from there, you're gonna drop here in the chat as well for everyone to read. But so far, if people have other questions, so is there any upwelling going near your site?
It should be. It should be. And actually, that's something I've been considering to explain this carbon-13 excursion that we observed at the intermediate site. But yeah, there is reports of upwelling in the zone, definitely. There's also another thing that you have to consider as well, now that I remember. So during AMOC slowdown, upwelling is another one of the processes that also gets affected by, because it also depends a little bit on this whole overturn in circulation. So I think, I'm not quite sure, I have to read more about that. But I think during AMOC slowdown, upwelling is reduced as well, because you no longer have this whole conveyor belt of.
So yeah, another question. Asking about the oxygen measurement using trace element.
Okay, so benthic foraminifera oxygen index and enhanced benthic foraminifera oxygen index is based on the total assemblage regarding the oxygen index. How about the oxygen measurement using trace elemental for a specific study? It is based on the total assemblage, yeah. I think I didn't mention this, but for the quantitative analysis, I picked between 200 and 250 forams per sample. It is based on the total assemblage. And how about oxygen measurements using trace element for a specific study? I'm currently exploring the manganese calcium ratio benthic foraminifera. I haven't elaborated much into it, but for what I've seen so far, they kind of also follow the trends of the reconstructions we did with the quantitative analysis. So it's something that I'm also working on the site.
I can't see anything coming from Facebook either. So I don't know if anyone has any last question.
So Sophia, I have a question, and it is wonderful that your presentation, because it shows us how important is micropaleontology in reconstruction of the paleoclimate changes. How do you end up working with foraminifera? This is also this is something that maybe for any of the GeoLatinas who are starting, working and learning about paleontology, maybe they would like to know what was your experience. So could you tell us a little bit more about that?
Yeah, sure. It is funny because when I started studying geology because I wanted to be a volcanologist, I really didn't like paleontology at all. And then I finally took my paleontology class. Back in my university, you only see one paleontology course in the whole bachelor's. And that's when I had a like a 2-week class of forums, and I fell in love with them. And I went to talk to the paleontology professor at the time, and I asked him if I could do my bachelor's dissertation with foraminifera. And he told me, yeah, I have some samples from the Guajira Peninsula in Colombia. Someone studied the Atlantic forams, but no one ever wanted to study the benthic foraminifera because they're very diverse and taxonomy is very complicated. So if you want to do that, it will be amazing. And I just started working with the benthic forams. It was quite an adventure. I worked with him for a couple of years. We actually published our paper on that research last year, many years after I finished college. And then when I started working for the oil and gas industry, they hired me actually because I knew about benthic foraminifera, which is not a very common thing among micropaleontologists in Colombia. And my curiosity drove me to pursue a master's degree in the University of Zaragoza, where I had the honor to work with Laia Leguet, which is one of the biggest experts on benthic foraminifera. And she basically taught me everything that she knew, and I fell even more in love with that for what you just said at the beginning, how important they are for us to understand how climate change has affected our planet in the past and the clues that it can give us for what can happen in the future. So after I finished my master's, I went back to Colombia. I kept working for the oil and gas industry for a couple of years more, but then I'm really fascinated by these applications that benthic forams have in climatic studies. So that's why I came here, and yeah, that's the story of how I ended up working on benthic foraminifera. It is the first time that I face geochemical proxies. I usually only did taxonomy and quantitative analysis, so it has been very challenging for me to do this research, but I have learned a lot. There's another question in the chat. Have you tried to calibrate the palette temperature with the recent species? Not really, but that is actually something that I plan to do because, as I mentioned at the end of the talk, we are expecting to measure magnesium calcium ratios in other species of benthic foraminifera, and we're gonna need to do that. But yeah, it's something that I plan to do soon.
Nice. Again, I don't see any other questions from Facebook, for example. If anyone has any other question, now is the time. So maybe not. So I don't know, Lilian, if you want to take over and finish the seminar.
Yes. Well, I want to show, I want to show you a small certificate that we made for you, Sofía. On behalf of GeoLatina, we are extremely proud of what you are doing and your research. Let me see, where is my? Yeah, so this is a certificate that we create for you, Sofía. If for the people who still have some questions, I would have to say that I just contact Sofía. You can follow her in her Twitter account or her email is Sofía, you can write it down on the chat and people can also know where to reach you. The certificate is actually showing the collaboration between the Paleo PERCS steering committees and the Education and Outreach Committees or GeoLatinas. We want to grant you this certificate and appreciate the work that you are doing. We will like you ready to invite you anytime that you have any new data and results and you want to share with us. Please don't even doubt in contact us, and we can include you, another Geo seminar as a continuation of what you started this time. For the people who are watching this Geo seminar, I would like to, this is the second season of the Geo seminar in GeoLatinas. We have a very successful first season, The second season is going to end in August. We still have few open dates. So if you are interested in giving a presentation in our seminar, please contact us and we will love to include you in the lineup of presentations. The third season is going to be from September to December. And that season, we already have a bunch of presentations programmed. So if you still, maybe right now, for the second season, you are not able to do the presentation, but you maybe consider to do it a little bit later on in the year. One more time again, please contact us. So here all the information of GeoLatinas. You can find us everywhere because we have many different channels in social media. And if you are not able to find GeoLatinas, at least if you find one GeoLatina, contact a GeoLatina, we will start making our connections from there. On behalf of GeoLatinas, and I think on behalf of PaleoPerc, I don't know if Pedro would like to talk from PaleoPerc. We want to thank all the audience, Sofía for her presentation. We will see you in the coming GeoSeminars.
From PaleoPerc, just for people that are used to our seminars, just let people know that next week is going to be the normal day and time, Tuesdays. So yeah, that's it. Thank you. Thank you everyone for inviting us for this collaboration. And yeah, it was great talk from Sofía as well. Thank you very much.
Yes, I don't know. Yes, thank you, Sofía. I don't know, Clara, if you want to say something.
No, I just want to congratulate Sofía. I was very impressed with her presentation. It's the first time that I listened to her research. It's not my area of expertise, but it's super important for the present and the future of everybody here. So I am very proud of you, Sophie, and hoping to see you in another GeoSeminar in the future. And thank you for the collaboration. Apologies for the issue with Facebook earlier. It was totally unexpected, but all good. We'll post it everywhere on social media, so I'm sure many people will watch this and be able to see and get inspired by Sofía. Thank you.
Okay.
Thank you. Thank you, Lilian, everybody, Pedro.
Thank
Bye.
you. Bye-bye.